Hello, everyone. Yeah, my name is Haosun, and based in Shanghai, responsible for Navitas EV Design Center now. And originally, I worked in Delta Power Electronics for about 16 years, and handled the whole Delta automotive power in China region. And my original work, I had about 6 years at about data center power supply design, and another 10 years for the automotive power design. So very glad to be here to introduce our data center design team and also our EV design center. So first is about our data center design team here. So we all know that the OpenAI or some other AIs grows very fast recently. And if we want to get a very smart AI, we must train them with a lot of data and a lot of energy. So then all this data will be stored in the data center and need the power supply system of the data center to drive the AI ICs. So that means our data center design team mainly focuses on this kind of power supply system of the data center, named the CRPS. So with the AI's growth becomes smarter, means that the power of the CRPS will become higher in the future. That means this kind of system must have the capability to provide the high power, high efficiency energy to the data center and the AI systems. So if we see the trend of this CRPS, so we can see that the GaN device and the SiC device will use its unique benefit in the high frequency, low power loss to support all these trends promoted here. So next slide, we can take some detailed numbers to say how this trend happened. So originally, the original design mainly with the silicon device, but with the old design, we can see that the efficiency only can get about the platinum requirement, mainly focused on the 94% or around that, and the power density lower than 100 watt per cubic inch. And also the peak power not so high, the hold time only stand about 10 milliseconds here. But now if we use the GaN or SiC, this kind of wide gap device design in the CRPS systems, with the efficiency we can increase it to some titanium requirement, high to about 96% here. And the power density can improve almost double, and the peak power can improve to about double here too. And also hold time, we also can improve it about 40% higher. But in the future, if we can use some better device like our GaNSafe and GaNSafe inside, we also can get even higher efficiency for the whole systems. And also the power density higher, because power density higher means that you can keep the same size but provide more power to the system. So, and also the peak power can be double, and also the hold time can be about 20 milliseconds. This is very important to the CRPS, means that if the power grid drop, you also have time to store your data in the system. And what's our data center design team do now? This is a demo I want to introduce to you all. So this is a CRPS named the 3.2 kilowatt system. This system is a 12-volt power supply to supply the whole data center. And it can transfer the power from the power grid to the low voltage to the data center and also the AI ICs here. So for this design, so we use our newest parts, the GaNSafe and the GaNSafe here for this system. And here I must highlight that so the system our design center made here is not a simple board. It's not a very simple board as the traditional semiconductor company doing originally. So this system is something like a real product, including all the mechanical, all the electrical, all the software, and all the reliability design concept inside. We name it as almost 18% to 19% real product. So with this design, we can see that for the GaNSafe part, we use it in the AC/DC stage, and the GaNSafe part, we use it in the DC/AC, the LC stage. And even with this design, even we compare it to, because we use the GaNSafe inside. GaNSafe had a much reliable driver inside compared to some discrete GaN design, and it can handle very high power. So even when compare it to the existing discrete GaN design we can find in the market, the power density also can be double higher than the original design, even with the discrete GaN here. And also the whole time we can get another 40% higher here. And for the power, because we can support high power with our packaging and with our GaNSafe device inside, so we can get a true 3.2 kilowatt power for our design. And the next demo for the system is the 4.5 kilowatt AI server. So we designed in our data center design team here. So the same part uses the AC/DC, GaNSafe uses the LLC. But you can see we can keep the same size with the 3.2 kilowatt here, but increase the power almost half to about 4.5 kilowatt. Means that the power density can be improved about 50% higher, from 100 to 138 watt per kmph here. And even the efficiency can be high to about 97%. If we compare to the original design with even with the discrete GaN or with the silicon or with some others design, all the power density, efficiency, and home time we can get a big improvement and all ahead of them. Yeah. And second is about our EV design center. Yeah, we all know that so EV is driven by the electricity. So in the EV system there is the OBC, there is the traction inverter to drive the car, OBC charge the car, DTC transfer the energy from the high voltage battery to the low voltage battery system to supply all the low voltage system in the vehicle. So our EV design center mainly focuses on all these high voltage power units in the EV here. And we all know that everyone wants the EV to run faster, to charge faster, but run longer. So SiC can be used in the traction inverter to get more power efficiency for the driving system. And GaN and SiC can be used in the OBC and DCC to make that smaller and lighter, to enlarge the range extend the range of the EV, and also can get more power in the same size compared to the original design. Yeah, so here the GaN and the SiC can play a very key role in this kind of system design, because GaN and SiC, they have the unique benefit in the, as I said, in the high switching frequency, low power loss, and a very reliable system, and a very low system cost here. And if we take a 6.6 kilowatt OBC as an example, we can see the trend of the automotive power, what happened during the past years. So the old design in that side is the very old design with some silicon-based design, OBC, 6.6 kilowatt. In that time, the power density is only about 1 kilowatt per liter. So very, very, very big one. And now the main product you can find, the mainstream product you can find in the market is focused on the 2.5 kilowatt per liter or 4 kilowatt per liter here. But in the future, it will become about 5 kilowatt per liter or even higher. Means that 5 kilowatt per liter means the product, the size is only about a hand size here. So with this trend, we can find that means that if we can keep the same size as originally, now we can go to almost the 5 times charging power than originally here, charging faster. This is a very key feature for these ones, and also reduce the weight to extend the range of the EV. So what our EV team build now? So this is also a high performance 6.6 kilowatt OBC combo we built recently. So for this one, we use our GaNSafe and GaNSafe inside, GaNSafe for the AC/DC. The frequency around about 100 kilohertz, not so high. But GaNSafe we used in this system is that we run the frequency high to about 1.2 megahertz. So with this kind of frequency, we can reduce the meg part very, very small, and to increase the whole power density to about 3.9 kilowatt per liter here, and also reduce the weight to lower than 5 kilogram. And another amazing point is that for the efficiency, you can see even with such a high frequency design, we also can keep even a little higher efficiency than the original and the traditional design. So this is the first time in the industrial level we can get that. Yeah. And also another one is about our 22 kilowatt OBC is the system. So this one is only with the GaNSafe inside because this is a three-phase system. So three-phase system means it's 800 watt bus, 800 watt here. So for these ones, we use the GaNSafe inside, and with the GaNSafe very high performance, we can build this demo to a very low size, only lower than 7.1 liters. So the footprint of this one is similar to an A4 size paper. So if you can imagine that, it's something like that. And the power density, we improve it to the 3.5 kilowatt per liter. So this is almost double compared to the existing product you can find in the market. And also the weight, we can keep it lower than 10 kilograms. And efficiency also can be high to about 96%. All these parameters are ahead of the existing product. You can find that here. Okay. Thanks for your attention. Yeah.